In this section, we're going to revisit motion of objects on surfaces. We're going to start to think about rough surfaces. In year 12, we looked a lot at smooth surfaces, where the assumption was there was no friction. And on a rare occasion, we had a rough surface and we were told the friction. But from here on in, we will need to calculate the friction for ourselves. So our standard model should have the weight and a reaction force moving vertically. And horizontally, we can have the friction, which I'm going to put as mu r, and any driving force. Now, I've put friction as mu r because friction is a function of the reaction force. Depending on the reaction force, the friction will change. Mu r is the coefficient of friction. The coefficient of friction is determined by the material that the two objects are made of. Highly polished metal will have a low coefficient of friction. It will be easy for that to slide over each other, compared to two pieces of rubber, where one was trying to slide over the other. They would have a high coefficient of friction. This will usually be given to you in the question, or it will be something that we're looking to find, but it is going to be an arbitrary value. Let's try this out with some actual values. So if we had a 5 kilogram weight being pulled with a force of 20 newtons on a rough surface where the coefficient of friction is 0.2, what would be the acceleration? So I've got my 5g and my reaction force, got my 20 Newton driving force, and here the friction should be 0.2 r. Okay, let's go ahead and do some resolving. First we'll go vertically, so I know the reaction force is 5g. Now we can go horizontally, and making use of Newton's second law, F equals ma. I can say that 20 in the positive direction, subtract the friction equals 5a, and just some rearranging from here. The acceleration is 2.04 meters per second squared. So up to now, in our calculation of mu r, we've actually been finding the maximum friction. Not every situation is going to call for the maximum friction. So we're just going to try and talk through when we might need to consider a value of friction that is not the maximum. Okay, so let's take this situation. We've got our weight and our reaction force as usual. The coefficient of friction is 0.4, and the driving force P, let's set P equal to 10. So if we were to go ahead and calculate as we usually do, we'll start by resolving vertically, and we get a reaction force of 5g. Next, we can resolve horizontally, and we're going to use mu r, or a maximum friction, is going to be 0.4 multiplied by the 5g, which altogether gives us 2g. Alright, so our resolving should give us 10 subtract 2g. That will be our resultant force, equals the mass times the acceleration. From here, apparently the acceleration is negative 1.92. Now, this doesn't make any sense. It suggests that the object, the particle, is going to be moving backwards, which cannot be true. The only driving force we have is P, which is trying to pull it forwards. It's either going forwards or it's not moving at all. A particle will not move unless the maximum friction has been activated. So that means the driving force must be larger than the maximum friction for the object to move at all. If the driving force is not larger than the maximum friction, then the maximum friction hasn't been activated. The actual friction that's activated will match the driving force. They are, after all, in equilibrium. The object is at rest, it's not moving, so the force to the right should match the force to the left. So you should always want to firstly compare the driving force to the maximum friction and get an understanding of whether or not this object, this particle, is in motion. If it's not in motion, it's in equilibrium. If it's in equilibrium, then the force to the right, the driving force, must equal the force to the left, the friction. The friction is not always going to be the maximum friction. So we need to be really clear on our understanding around that. Okay, so let's go again and see how we should have approached that last question. So the driving force is 10. The friction I'm going to model is 0.4 R, which is the maximum. We're going to consider whether or not it's moving. Weight of 5G and our reaction force. Resolving vertically, reaction force is 5G. A comparison of the driving force and the maximum friction lets me know the driving force is less than the maximum friction. So actually, this particle will not move. This particle is not in motion, so it's in equilibrium, which then means that the friction must equal that driving force. The friction equals 10 newtons. Okay, no need for Newton seconds, no need for F equals ma. The friction is just 10 newtons. Acceleration is 0. Okay, and just one more case to consider. What would happen if the driving force was exactly 19.6 and the maximum friction, once again, is 2G, so 19.6? What if these two matched each other? If we have this situation, we're still in equilibrium, but this is a specific type of equilibrium. This is what we call limiting equilibrium. This means that any increase to the driving force will make this object move. It's right on the verge of moving. So it's slightly different to just equilibrium. It's limiting equilibrium. Okay, and for completeness, let's do one where the object is in motion. All right, so as always, we'll put our forces on. Got our 5G and my reaction force. Let's increase this driving force. Let's make it 30 newtons. All right, so a quick comparison. The driving force and the maximum friction. 30 is larger than 2G, so this object is going to move. It's going to be in motion. So we can go ahead and make use of Newton's second. So resolving horizontally, we get our resultant force of 30 minus 2G equals the mass times the acceleration, and some rearranging gets us an acceleration of 2.08 meters per second squared. All right, so the point here, always make sure that we made a comparison to decide which state the object is in. Is it in equilibrium? Is it limiting equilibrium? Or is it in motion?